Hi everyone, this is video number 6A of the Regents Chemistry curriculum. Today we are going to learn how to name and write formulas of different compounds. So if we see a container that contains a particular compound, we know how to label it correctly. So let's get started. Here are some questions. If you know the answers to these questions, that's great. If you don't, please hold on tight. You will know the answers to all these questions by the end of this video. Pause the video. Think of the answers. Write them down. Let's get started. All right. So our lesson today is about naming and writing formulas. Before we can do all of this, we can probably first answer the question, what are the types of formulas? There are three types of formulas. Molecular formulas, which contain the symbols and the number of moles of each atom. For example, N2. So here I know that I have nitrogen, the symbol, and I have 2 of it. This can be calculated using the following formula. Given molecular mass divided by empirical mass times the given empirical formula. So a molecular formula could be a multiple of an empirical formula. I'll explain that in a second. So an empirical formula is the simplified form of a formula, while a molecular formula is the kind of like the magnified form of that formula. So let's take, for example, P2O5. This is a very simplified formula. Diphosphorus decoxide, that's the name of this. Diphosphorus pentoxide, that's the name of this formula, diphosphorus pentoxide. If I take this formula and multiply it by 2, I'm going to have P4O10, and that would be tetraphosphorus decoxide. Deca for 10, tetra for 4, while in the beginning we had di for 2 and pent for 5. I'll tell you in a second where I got these from, but for right now, know that this is an empirical formula because it's a very simplified formula, and this is a multiple of that formula, so this would be a molecular formula because you can simplify this further. Now, it's also important that we understand that an empirical formula can also be considered a molecular formula. So this is also a molecular formula. Okay? But a molecular formula, just like the one I wrote earlier, P4O10, this is only molecular. This is not empirical, because empirical means it cannot be simplified any further. Okay? This is also molecular. Okay. So let's say for example I have I'm given the empirical formula CH4. I clearly cannot simplify this any further. CH4, you cannot, there's no greatest common factor for me to divide the C and the H by to get a smaller or simpler formula. So this cannot be simplified any further. Now, if I'm given CH4 as the empirical formula, okay, and I'm given the mass of the molecular formula. So let's assume that the mass of this molecular formula is going to be 32 grams per 1 mole. Now, the question may ask you, what is the molecular formula that has a mass of 32 grams per 1 mole and its empirical formula is CH4? Again, what is the molecular formula? What is the molecular formula? Figure out what the molecular formula is. which mass is 32 grams per 1 mole, and its molecular formula is CH4. So to answer that question, you simply just follow the me formula, m divided by E times E. So here your molecular mass, m stands for molecular mass, and that is going to be 32, given to us. E is the empirical mass. Here I have EMMT. What I mean by EMMT is you can actually perform an EMMT calculations like this. So E is the element, M is how many of that element you have, the other M is the mass, so how many, the mass, and T is the total, which you get by multiplying the M&Ms. So M times M, how many you have times what the mass of each is, that'll give you the total. So if I was to do that for the CH4, the elements are C and H. These are the elements. How many of the C's I have for CH4? There's only one C, so that's one C. There are 4 H's. Here are the 4 H's. Okay. And then what's the mass of each one of them? One C has a mass of 12. And for H, each hydrogen has a mass of 1. So the total, multiply the M&Ms, 1 times 12 gives me 12. 4 times 1 gives me 4. Add those together, 12 plus 4 gives you 16 grams per 1 mole of CH4. So one of the CH4, one of the molecule CH4 will weigh 16 grams. That's what 1 mole means. One quantity, one of the CH4 weighs 16 grams. So we go back to our calculations here. So 32 grams was the given mass of the molecular formula, that unknown formula that I don't know. 16 grams E, M over E. 16 grams is the mass of the empirical formula, which I just calculated right here. Empirical formula CH4, I calculated its mass as 16. By the way, you don't have to do the EMMT. This is just a it's just used for clarification. You can just get the masses. So the mass of carbon is 12. You look at the periodic table, by the way. So here's periodic table. Carbon has a mass of 12. So 12.011, you round it off to 12. Hydrogen has a mass of 1.000794. You round it off to 1. And that's how you get the masses. So going back to here. And then, so obviously you'll multiply. So the mass of one hydrogen is 1. You got 4 of them. So the mass of the 4 hydrogens is 4. The mass of one carbon is 12. There's only one of it. So the mass of that carbon is going to be 12. 12 plus 4 gives me 16 grams for 1 CH4. 1 mole of CH4. So to figure out what the molecular formula is, going back to here, the molecular mass is 32. The empirical mass I calculated is 16. So 32 divided by 16 gives me a total of 2. This means that this is the factor. So your molecular formula is 2 times your empirical formula. So your empirical formula was CH4. 2 times your CH4 will give you C2H8. C2H8 is going to be your molecular formula. That's really all that is. So that's how you convert, or that's how you figure out or identify what your molecular formula, if given your molecular mass and given your empirical formula. To go backwards, meaning to find the empirical formula from the molecular formula, all you have to do is divide by the greatest common factor. So let's say I had my C4H8. This is your molecular formula. And you want to calculate your empirical formula. Then I take my C4H8 divided by the greatest common factor. In this case, the greatest common factor is 4. And that will give me my empirical formula, which would be CH2. Ladies and gentlemen, that's pretty much it about the empirical formulas and the molecular formulas. There's another way to calculate the molecular formula if given the percentages. If given the percentages, example here, 53%, 47%. If you have 53% of aluminum, 47% of oxygen, what is the empirical formula? You can just assume that we're talking about 100 grams, and then 53% means 53 grams of aluminum, 47% means 47 grams of oxygen, okay? And you can figure out how many aluminums and how many oxygens you have by dividing by the mass. So 53 grams of aluminum means that you have, each aluminum weighs 27 grams. So if you have 53 grams, you have 2 aluminums. So that's Al2. And if you have 47 grams of oxygen, then the mass of each oxygen, according to the periodic table, is 16. So 47 divided by 16 will tell you that you have 3 oxygens. So your formula is Al2O3. Now the third type of formulas is the structural formula. So the first type was empirical, the second type was molecular, and the third type is going to be your structural. Structural formula just simply displays how atoms are bonded to each other. For example, the N2 molecule atoms are actually bonded this way. We'll learn more about how to draw structural formulas when we get to Lewis dot diagrams and we get to organic chemistry. Okay, now naming and writing. We're going to first talk about naming and writing for ionic compounds, and then we're going to talk about naming and writing for molecular compounds. So for naming and writing of ionic compounds, if the compound is binary, meaning it's made of 2 elements only, your name must always end in IDE. Take, for example, NaCl. Na is sodium. Cl is chlorine. But I can't say that the name of this compound, NaCl, is sodium chlorine. My ending has to be chloride. So take off the INE and make it chloride. So this would be sodium chloride. All right. Continue on. If a metal has multiple charges, reverse crisscross to identify the charge of the metal and use Roman numerals. So let's say, for example, here, Fe2O3. Fe2O3. I know iron has multiple charges. I look at my periodic table and I find out that my iron has a charge of +2 and +3. So it does have multiple charges. Na, on the other hand, only has a single charge. Calcium, a single charge. Scandium, a single charge. But iron, along with manganese and chromium and vanadium, they have multiple charges. So you have to use a Roman numeral to identify the charge of that metal. We only care about the metal. We're not really worried about the non-metal. So to identify the charge of iron in this case, I will reverse crisscross. I will take my 3 and crisscross it up this way, and I'll take my 2 and crisscross it up that way. So what does that tell me? That tells me that the name is iron, Fe for iron, and 3 is the Roman numeral that represents the charge of iron, which I just identified by reverse crisscrossing. An oxide. Notice I don't have to write a Roman numeral for the nonmetal. Nothing. You'd never do it. Don't do it. Okay, so just iron, 3 oxide. If you don't have something to reverse crisscross, for example here, FeO, there's nothing to reverse crisscross here. You know that FeO has no subscripts because whatever charge oxygen had was cancelled out by the charge that iron had. So if oxygen charge was negative and iron charge would have had to be positive, and the magnitude of these charges had to be the same as well. So let's take a look at what the charge of oxygen is. Oxygen, according to the reference table, has -2 charge. That means in order for me to have FeO, which is a compound that has absolutely no subscripts, so oxygen is -2. In order for me to have FeO, which is a compound that has no subscripts here, iron charge would have had to be +2. So now I have concluded that iron has a charge of +2, hence why the name is iron 2 oxide. Again, IDE because it's only 2 elements, Fe and O. Now if you have ternary compounds, meaning 3 or more elements, that is when you that happens when you have a metal combined with something, a polyatomic ion from table E. Okay? So, if a metal has multiple charges, you're going to reverse crisscross and so on. But let's first take the first scenario. Let's say, for example, CaSO4. So, I have calcium over here. Calcium only has a single charge, so I don't need to use Roman numerals. If you use them, that's fine. It's not a big deal here, but you should probably not do that. So calcium has a single charge. Okay, so you don't need to use Roman numerals. Now, SO4 comes from table E, polyatomic ions. So here's table E. SO4 has a charge of -2. And the name of SO4 is sulfate. Ending is ATE. Now, if I'm writing the name of CaSO4, all I do is write calcium, and I copy the name of this SO4 as it is. I'll just say calcium sulfate. You don't need to change endings. You don't need to do anything. So if it ends in ATE or ITE, you don't have to worry about changing anything. Okay? Notice I did not use Roman numerals here again because calcium does not have multiple charges. Now, what if I had Fe2 SO4 3? In this case, I know iron has multiple charges. It has a +2, like I mentioned earlier. It has a +2 and a +3. So I have to specify the Roman numeral. I'll do the same thing that I did previously, reverse crisscross. But in this case now, I'm going to reverse crisscross the number that's outside the parentheses. Don't touch the number that's in the parentheses. So this is the number that you're reverse crisscrossing. The number that's in the parentheses is not considered a subscript. It's pretty much just part of the SO4. If you take that 4 out, it's no longer sulfate. It's just something else. So don't touch anything that comes from table E. Those numbers that are on table E, consider them like ligaments for the actual polyatomic ions. If you move them, you're actually kind of like cutting them in half, or you're messing them up. So don't touch those numbers. You have nothing to do with these numbers. If there's a number outside the parentheses, then you can reverse crisscross it to identify the charge of the metal iron. And obviously you'll reverse crisscross the other one too, but you don't really need to worry about the charge of the polyatomic ion when it comes to naming. So this would be iron. The charge of iron after I reverse crisscrossed is +3, so this would be iron 3. And then SO4 is sulfate. Copy paste sulfate. Now what if I don't have subscripts? Example FeSO4. Here you cannot consider this for a subscript. This is not a subscript. This is part of SO4. So there's nothing to really crisscross here. You cannot reverse crisscross anything. So what you do is you look at sulfate. The charge of sulfate is -2. Therefore, the charge, if sulfate is -2, so all of this sulfate is -2, that means Fe had to be +2 in order for me to get no subscripts here. Okay, so this name would be iron 2 sulfate. That's pretty much it. Iron 2 sulfate. That would be the name of that. Some things you should know. If you have numbers on top, for example, here, Fe plus 2, SO4 minus 2. These numbers, these charges on top, we call them superscripts. Superscripts. Superscript. And if you have numbers at the bottom, example here, let's say Fe2O3. These numbers at the bottom, we call them subscripts. Subscript. They tell us how many atoms we have. So the superscripts tell us the charges. The subscripts tell us how many atoms we have. And then there are coefficients. Coefficients are actually numbers that go before the entire compound. Let's say you have Fe2O3 and you have 3 here, big 3 before the Fe2O3. This tells me that I have 3 of the iron 3 oxide compound. So that tells me what is the quantity of the compound. I have 3 moles. 3 moles of the iron 3 oxide. Okay? So going back to here. So that's pretty much it for naming ionic compounds. Now when it comes to writing formulas for ionic compounds, you're going to do the same exact thing that you did earlier. For example, let's say here magnesium fluoride. If I want to write the formula of that, magnesium is, first you write the ion formula, which is you pretty much identify the charges. So Mg is +2, F is -1. And then you crisscross to figure out the compound formula. So so here it goes in a little bigger. Mg is +2 for magnesium, F is -1 for fluorine. You crisscross and you'll get Mg, the 1 goes down here. You only crisscross the numbers. You don't crisscross negative or positive. You only crisscross magnitudes. So Mg is 1, F is 2. The 2 from the magnesium went down to the other side, while the F from the fluorine went down to this side. So you get Mg1, F2. You don't have to put 1. Obviously, there's 1 Mg. You don't have to write 1 Mg1. So you can write this as Mg F2. If you write it, that's fine. If you don't, no big deal. Okay. For iron 3 oxide, same thing, but now you have the charge given to you. So this is Fe. The charge of iron is +3. They specified it for me. The Roman numeral will always be the charge of the metal. And then oxygen, you can get the charge of oxygen from the periodic table, and that's -2. You crisscross, and you will get, remember, you crisscross the numbers, you don't crisscross the charges. You don't crisscross positive or negative, you only crisscross the 2 and the 3 in this case. So you'll get Fe2O3. That will be the formula for iron 3 oxide. If you were doing it for polyatomic ions or ternary compounds, such as iron 2 sulfate, make sure you remember to use parentheses. For example, iron has a charge of +2. Sulfate has a charge of -2. Well, in this case, the +2 cancels out with the -2. So you'll only get FeSO4. If you had iron 3 oxide, iron 3 sulfate, so let's say you had Fe +3 and sulfate -2, then when you crisscross, you're going to get Fe2. Use a parenthesis because now your 3 is actually going to go to the SO4. It's not going to go to the O. It's not going to go to the S. Your 3 is now going to go to the SO4. So you're going to get Fe2SO4, 3 of the SO4. 3 of the SO4. Okay? So that's how we do it that's how we write formulas for ternary compounds. Okay? Remember, never change the endings for ternary compounds when it comes to naming. You only change the endings for binary. Make sure it ends in IDE. Now for molecular compounds, naming rules, before I go into the molecular compounds, let me just review with you the Roman numerals. So this is number 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, 8, This is 7. This is 8, 9. You're not really going to go above 9, so you're fine. You can do 9 like this, and I think you can do 9 like that too. That also works. And that's 10. Okay. Now, when it comes to molecular compounds, for molecular compounds, if you're naming them, you got to use prefixes. The prefixes that you have to memorize are going to be mono for 1, di for 2, tri for 3, and tetra for 4. From here on, penta, hexa, hepta, octa, nona, you can just get them from table P. You only have to memorize mono, di, tri, tetra when it comes to naming molecular compounds, but everything else after that, you can just get it directly from table P. Here's table P. So 5 will be pent, penta, hexa, hepta, octa, nona, deca. You don't want to use these when naming molecular compounds. These are used for naming organic compounds. In place of them, we're going to use mono, di, tri, tetra when naming molecular compounds. Okay, naming molecular compounds is actually very straightforward. All you have to do is use the prefixes to identify how many atoms you have. So let's say N2O, that's 2 nitrogens. I would say di, nitrogen. 1 oxygen, I would say monoxide. Let's say I'm given another example. CO. 1 carbon, I would say carbon. 1 oxygen, I would say monoxide. We don't usually write mono before the first element. We just write carbon. We don't need to say mono, carbon, monoxide. We only write mono for the second or third element. We don't write it for the first element. Okay, what if I'm given CO2? I would say carbon, 2, dioxide. Okay? Ending for molecular compounds usually is just IDE. And now if I was given backwards, if I was given the formula and I was asked to write the name, if I was given the name and I was asked to write the formula, for example, let's say I'm given CH4, again I use prefixes. No. The name, if I'm given the name, so I'm given carbon, tetra, chloride, let's say. Carbon tetrachloride. So this is the name, carbon tetrachloride. Now if I have to write the formula of that, I simply just write down what I see. Carbon is C. How many carbons do I have? Is there a prefix? There's no prefixes. So carbon is C. Tetrachloride, that means I have 4. Tetra's 4. 4 chlorines. So I'm going to say C, 1C. Cl4. 4 chlorines. So the name of the formula for this is going to be CCl4. That's pretty much it for writing molecular compounds. Please don't ever give prefixes if you see a metal in a compound. You should never use the prefixes if you see a metal in a compound. Okay? Now, that's pretty much it for naming and writing ionic and molecular compounds. Let's go back to the questions. See if you can answer these questions. Pause the video. All right, thank you.